All right, so let's look at checkpoint 12. So for this first question, so we have four-sided dice. They're all fair. So we want this capital X to be a random variable that specifically captures the number of twos that I roll when I roll all four of these dice. So the first thing I want to do is to set up a probability distribution which shows, basically the full spectrum, you know, of all the possible values of X. So what are all the possible values of X that I can have? It's everything from, all the integers from 0 to 4. So let's just take these one at a time. So what's the probability that X equals 0? So if these are fair dice, then I have a 1 in 4 chance of rolling any given number, which means I don't want any of these to hit. I don't want any of these to land on 2, which means they have a 3 out of 4 chance of doing that. So this probability is 3 out of 4 to the power of 4. So what is this probability? Or should I just keep it as a fraction? Maybe I'll just do that. So 3 to the 4th power is 81. 4 to the 4th power is 256. Okay, moving on. What's the probability that I have exactly 1? Now, this is a little more complicated because, okay, I want to roll exactly 1, 2. But it's not as simple as saying, okay, that's 1 out of 4, right? Well, that's part of it. But that means I also need to have the other 3 be not 2. So that means I need a 3 out of 4 chance to the power of 3. So basically, I need 1 success and 3 failures. So that's why I have both of these factors here. I have a 1 in 4 chance of getting a 2, and I have a 3 in 4 chance of getting anything else. But I need that to happen 3 times over. But I left a space here because there's one thing we're missing. I have 4 spinners, and there's 4, so there's 4 possible ways. There are 4 different spinners that can give me this too. So I have to account for that. So basically, there are 4 combinations here. And I have to think about what notations have I been showing you for this. There are 4 combinations, so let me make some more room for myself. So of those 4 spinners, I want one of them to be a 4. So basically, of a list of 4 objects, I'm going to choose one. That one object has a 1 in 4 chance of succeeding, and I want the other 3 to be failures. So here's my probability. So what is 4 choose 1? That's going to be 4. So 4 times a fourth times 3 cubed over 4 cubed. That'll be 27. So I'm just going to keep it. I'm not going to simplify anything because I really like that. Have that. Let's just try to keep a common denominator of 256 here. So this is going to be 3 to the 3 is 27. 4 to the 3 is 81. So this comes out to be 4 times 27, which is the 108. Am I wrong about what 4 to the 4th power is? I'm wrong about what 4 to the 3rd power is. This should be 27 over 64. So this should be 108 over 256. Let me just double check that again since I kind of goofed it up. This is 4 times a fourth times 27 over 64. Okay, so I feel good about that. So 81 over 256, 108 over 256. All right. Next, what's the probability that I roll 2? So this thing right here, I didn't really talk about this, but throughout one of the videos, you probably saw that formula for how to set up like a Bernoulli trial. That's basically where this comes from, is that um okay, so I want 2 successes now. So what's my probability of a single success? That's a fourth, and I need 2 of those. But I also need 2 failures. What's the probability of a single failure? That's 3/4, but I need 2 of them. But I also need, and I didn't give myself enough room for this. I also need a 4 choose 2 combination here. Because of those 4 spinners, I need 2 successes to show up somewhere, and there are 6 ways that can happen. So the number of combinations here is 6 times 1/16 times 3/4 squared, which is 9 over 16. So what does this come out to be? This is 6 times 9 is 54 over 256. What's the probability of 3 of these things? So now that we're thinking about this in terms of Bernoulli trials, we can kind of set this up along that framework. So of these 4 spinners, I need 3 successes. So this is 1/4 to the power of 3 times 3/4 to the power of 1. 4 choose 3 and 4 choose 1 are going to be the same value. That's 4. 1/4 to the third power, that's going to be 1 over 64. 3/4 to the 1 is 3/4. So 4 times 3, that's going to be 12. So 12 over 256. And then finally, what's the probability? So one thing I will point out here is that I didn't use that combination term for x for when the random variable x was equal to 0. So did I forget it, or did I get away with it? Well, I mean, yes and no. I don't really need it, and I'll show you why. Let's be really specific and include this time. Let's do 4 choose 4. So let's think about it this way. If I have a combination of 4, I want a combination of 4 things, and I have 4 things to choose from. How many ways are there to choose all 4 of them? There's only one way to take all of them. And similarly, if you're going to make a combination of 0 things, and you're going to choose those from 4, there's only one way to do that. There's only one way to take nothing. So same kind of idea here. 4 choose 0 is 1. 4 choose 4 is going to be 1. So leaving that term off is going to be basically you're multiplying by 1 essentially. So this is going to be 1/4 to the 4 times 3/4 to the 0. So this is going to become 1 over 256. The last thing I'm going to do here is to make sure that when I add all my numerators together, they really do come out to add up to 1. Because that's what a probability distribution should do. If I take all my possibilities and add them together, they should make up, they should add up to 1, because that's certainty. And they do. So I do feel good about this probability distribution. So these are my distinct probabilities. So higher probabilities that I throw fewer 2s. Okay. So that's kind of the hard work for this question. Now that you have that, answering these other questions is relatively simple. So now, what's the probability that x is at least 1? So the probability that x is at least 1 is, now I can add these things together, because the probabilities that I found in A, these are all exclusively, I threw exactly 0 2s. I threw exactly 1 2. I threw exactly 2 2s, and so on. So now that I have this at least probability, I can add these things together. So what's the probability that I threw at least 1, 2? That's 108 over 256 plus 54 over 256 plus 12 over 256 plus 1 over 256. And what does that come out to be? 162, 174, 175 over 256. And I'm realizing that you probably can reduce a lot of these. I am not, because I think it makes it easier to kind of compare these to each other if they're all over the same denominator. But if your answers are reduced, that's perfectly fine. All right, and finally, what is the probability of x less than 3? Probability of x less than 3. So what members of my probability distribution do I care about this time? So this is not a loose inequality like the last one was. This is a strict one. So I care about 0, 1, and 2. I cannot permit the 3 in this case. So I want 81 over 256 plus 108 over 256 plus 54 over 256. So the probability that I roll 2 or fewer heads is going to be 189 plus 54, which is 243. Might as well double check. 81 plus 108 plus 54. Yeah, 243. So very, very high. All right, that's all for question 1. Moving on to question 2. So Caitlin Clark, no longer the point guard for the University of Iowa. But she shot 86% on free throw attempts her senior year. So basically we're going to treat that like a probability, her success probability. So if she shoots 20 free throws in a game, what's the probability that she makes exactly 16 of them? So when you're shooting a free throw, we can treat this like a Bernoulli trial, because shooting a free throw has exactly 2 outcomes. It's either good or it's not. So what's the probability? So let's say that our random variable stands for her number of successes. So let's say the probability that she makes exactly 16 free throws. So we can set this up like a Bernoulli trial, just like I did in the last question. So I'll start with the successes and failures first. I need 16 successes. So what's the probability of a single success? The probability of a single success is 0.86. And how many successes do I need? I need 16 of them. What's the probability of a failure? So whatever 1 minus our success probability is, that's 0.14. And I need 4 of those. And I miraculously left no room for this again. I keep forgetting what notation you all are used to with combinations. So I don't care which 4 she misses, or equivalently, I don't care which 16 she makes. So that's why I need to look at the combination here. So basically I have a combination here, 20 choose 16, which is a thing that I would rather not calculate by hand. Thought this would be easier to look up. Okay, so that's going to be 4,845 times 0.86 to the 16 So your answer is probably gonna be a lot better than mine if you are storing all these numbers instead of rounding them like I am having to do. So 0.08953 and 0.14 to the power of 4. Okay, so 0.000384. All right, so probability that I am getting here is 0.167. So probability she makes exactly 16 is 0.167. All right. Next one. What's the probability she makes at least 18 free throws? Okay, so this is a little more complex. This is an at least probability. So probability that X is at least or greater than or equal to 18. So how many cases do I have to consider here? This is going to be probability that X is equal to 18, plus the probability that X is equal to 19, plus the probability that X is equal to 20. So let's go ahead and do that. So what's the probability that X is equal to 18? We can set it up the same way. Probability that X is equal to 18. So let's set up that calculation. That is the combination. So 20 choose 18 times 0.86 to the power of 18 times 0.14 to the 2. So let's go get these numbers one at a time. Point 0.06622 0.14 squared and 0.16. So the chance that she makes 18 is 0.2466. Okay, so that's one thing we need. What about the chances she makes 19? So that's 20 choose 19 times 0.86 times 18 times 0.14. Not 18. 19 times 0.14 to the 1. So I know from the way that combinations work that 20 choose 19 is the same as 20 choose 1, which is 20. So 20 times 0.86 to the power of 19, which is 0.05695. This one I can just store. So this one comes out to be 0.1594. And then finally, what are the chances that she makes every single one? So this is a 20 choose 20. There's only one way for that to happen. Times 0.86 to the 20 times 0.14 to the 0. So this is just going to be purely what 0.86 raised to the power of 20 is. So that's 0.0480490. So let's go ahead and add all those together. Plus 0.1594 plus 0.2466. All right, so all told, the probability I get is 0.4550. So the probability that she makes 18 or more of these free throws it's high. It's 45.5%. All right, and then finally, part C. What are the chances she makes fewer than two? So what does fewer than two mean? It means basically 0 or 1. So let's find those probabilities. So what's the probability that she makes 0 out of 20? So that'll be, 20 choose 0 times 0.86 to the 0 times 0.14 to the 20. So this is going to be incredibly small. So that's basically 1 times 1 times 0.14 to the 20. And I get a number that's 8.37 times 10 to the negative 18. All right. And what is the probability she makes 1? So that's 20 choose 1 times 0.86 to the 1 times 0.14 to the 19. And I'm just going to have enough room, aren't I? So 20 choose 1 is going to be 20. 0.86 to the 1 is 0.86. And what's 1.14 to the 19 times 20 times 0.86? Give this to me in scientific notation. All right, unless I lost count, I believe what I have is this, about 1.04 times 10 to the negative 15. So incredibly low probability that Caitlin Clark takes 20 free throw attempts and makes less than 2 of them. All right, so that's all for question 2. Moving on to question 3. So in their history, the Diamondbacks have played 25 full seasons. And these are the numbers of wins they've had in their history. Let X be a random variable, which stands for the number of wins in a given season. So let's find the mean and median of X. Okay, so if we're going to find the mean and median, really, if we're going to find the median, I think something that's worthwhile for us to do is to list these in either ascending or descending order, whichever one we want to do. So let's do ascending order. So let's start with the 50s. I see a 51 and a 52. Are there other 50s? I don't think so. So 51, 52. All right. How about 60s now? I see a 65, a 64, a 65, a 69. I think that was it. All right, so I saw 64. 2 65s. 65, 65. 69. Okay, that's all for the 60s. What about 70s? There's a 70, 79, 77. Okay, so I'll cross off the 70. I only see one of those. All right, then what? 74, is that next? Looks like it. All right, then 76 is probably next. 76, 77, 76, 77. Let's see, a 79, is that next? Yeah, 79. All right. Is there an 80? I see a couple of 81s. 81, 81, 82, 82, 81, 81, 82, 82, 85, 85, 85, 85. Oh, horse. You knew I was going to make a mistake here. Let's squeeze an 84 in here. 84, 85, 85. And then 93, 94, 100. 93, 94, 100. That's not enough. Okay. So 51, 52, 64, 65, 65, 65, 65, 69, 70, 74, 76, 77, 79, 81, 81, 82, 82, 84, 85, 85, 92. I missed another 84 tonight. This is a bad day for me. Right. Does that make sense? This is gonna make a riveting video. Let's try it. Let's count them off one more time. 51, 52, 64, 65, 65, 69, 70, 74, 76, 77, 79, 81, 81, 82, 82, 84, 84, 85, 85, 92, 93, 94. There's a 90 in there. $90, $92, $93, $94, $98, $100. Okay. I'm like 90% sure that's right. And we're just going to act as if it is. Okay. So what was the point of doing all that? That was to find the mean and the median. Really, that's to find the median. So what is the median? The median is found by lining all these things up and finding the one that's in the middle. So how many data points do I have here? There are 25. So what's the midpoint going to be? So the midpoint is going to be of 1 and 25. 1 plus 25 is 26. 26 divided by 2 is 13. So the 13th element here will be the median. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the median is 81. Okay. We were also asked for the mean. How do you find the mean? So mean is probably the one you think of when you think of the word average. That's the one that's found by adding all these things together and then dividing by the number of values you have. So I'm going to add all these values together and divide by 25. All right. And my mean is 78.92. So these are my median and my mean. Right. So that's part A. And then part B says to draw a histogram of this data. So, and it looks like I want to use basically decades. So 51 to 60, 61 to 70, and so on. So let's go ahead and do that. So let's start. So how many bars am I going to need basically? So that's 51 to 60 to 70 to 80 to 90 to 100. Okay. And I'm going to make them all the same width because they're all by tens essentially. And I'm also going to use like a representative value. So when you draw histograms, you usually have, actually, you don't need to because we're not going to make calculations necessarily based on it. If you're going to, you kind of have to use a representative value. But for these, I'm just going to say, right, this is 51 through 60. This is 61 through 70, 71 through 80, 81 through 90, 91 through 100. And that's as high as we need to go. So, and what are my frequencies? So for 51 to 60, that is going to be, let's make sure it's what's the most I'll need? So the 50s is going to be 2. I guess we can make some notes down here. 2. For the 61 through 70, 1, 2, 3, 4, 5. 71 through 80, 1, 2, 3, 4. 81 through 90, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's got to be it. And then 91 through 100, 1, 2, 3, 4, 5. So just to make this easy, yeah, we can count it up. This we can just count up to 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's probably too high. Let's not make this more of a mess than it already has been. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so for this first category, we need 2, then 5, and here we're just basically using the data to fill the rest of this in, making sure all these bars are, you know, perfection is not something I'm going to demand of you, but they should, at least in relation to each other, they should make sense. For example, what I mean by that is the bar for 71 through 80 should be noticeably shorter than the one for 61 through 70. And the one for 81 through 90 should be significantly taller than all the rest of them. All right, so that's a good histogram for this data set. So that is all for checkpoint 12.